I'm going to calculate solar potential in my town with lidar and space math in under 4 minutes. So we started in part 1 with a hill shade, which is kind of a 3D vibe of my city, but now let's use some space math to get some numbers on insolation. So the area solar radiation tool uses the hemispherical viewshed algorithm, and it needs certain parameters to be able to do this. It needs things like latitude, because where we are on the globe, it kind of matters to the sun. And then let's also run this to get an estimate over the entire year. In addition, let's calculate it with 32 sun angles that will hit these 3D surfaces over the course of each day. And then let's run it, and 3 days, 8 hours, 54 minutes later, here we go. We have an output. Each of these pixels is going to give me a value that tells me the kilowatt hours per meter squared. And you can see all my south-facing roofs are at a higher level than my north-facing roofs, which is what we would expect. And you can also see here that there are trees that are shadowing different parts of a roof, which would give a lower solar insolation or solar radiation estimate. But now we have to make 2 new surfaces so we can figure out what roof lines are actually available to put solar panels on. So we have a slope and an aspect. The first one showed the slope and a value between 0 and 90 degrees, and this is the aspect. Anything in a pinkish red will be north facing. And we'll use these things to eliminate portions of these roofs that would not be ideal for solar panels. First, we're going to use our slope surface and a conditional raster tool to eliminate any results that have a steep surface. And then we're going to remove any areas that have a low solar radiation value. To decide this cutoff for what counts as low, we're going to look at our result histogram. And it looks like we get most of our high values at around 1,300 kilowatt hours per meter squared. So, removing anything below that value, we can then move on to use our aspect surface and a conditional raster tool again to remove any north-facing angled surfaces. And finally, we'll have some suitable areas where solar panels can go. That's not too steep, it's not too low, and it's not north-facing. Now at this point, I was so excited I had to take a walk around the block because we have all the suitable areas for solar panels in my city, along with the solar radiation calculations these surfaces could collect. But let's keep going and make it more real for people. So we have these amazing raster results, but now we need to compute statistics per building and see how much actual electricity we could gather. So we can run a zonal statistics as table tool and get the suitable area and the mean insolation values per building. And then we can remove any buildings that have a suitable area of below 30 meters squared because solar panels need at least that much space. And you can see in the green here that these are buildings that had some solar insolation results, but they didn't quite make that spatial cut. We can then calculate the usable solar radiation per building in megawatt hours by using the area and the mean value that we had already calculated. And finally, from that step, we can estimate actual electrical output. Now, the EPA conservatively estimates solar panels have a 16% efficiency rate, and using that, we can estimate the number of megawatt hours per building a solar panel installation would actually produce, which is different than solar radiation. Now, with that value, we can symbolize each building by its estimated solar electricity output. And the average US household uses 11.8 megawatts of electricity per year. And with this analysis, I now know that in my town, 87% of buildings, if solar panels were added, would meet or far exceed that rate. And so we could pretty much rule the world. Thanks for learning about GIS with me, and remember to look into renewable resources. And a huge thanks to Esri's Delphine Khanna's analysis methods. Couldn't have done this without you.